if for some reason the pressure changes, the speed has to change, or vice versa. Let me show you a couple other examples before I do a numerical one and close out the unit. So here's a classic example. This suction, you can don't have to have a special chemistry faucet with a little rubber tube with a side outlet. What you can do is in the morning, you're taking a shower. Same thing is happening to the air in your shower stall. The water molecules increase their speed a little bit and the pressure drops. So the pressure is slightly decreased in the shower stall. You can still breathe, of course. It's not a minuscule effect. But the pressure is dropped. But the way you can see it's occurring is when you have the atmospheric pressure on the other side of your shower curtain, which way is the shower curtain going to experience a force? Always toward the lower pressure. So your shower curtain starts to creep in on you. The faster the water flows out of your shower head, the worse it is, right? You have to wet it, stick it to the side of the tub, right? So that's one example. Another example, here's a truck. Let's say you're late for class and you want to pass that truck. Well, a truck is a big aerodynamic beast. When it cuts through the air, it causes the fluid to flow with it. And if it has fast speed fluid on the sides, the pressure will drop. And the atmospheric pressure on the other side of your car will seemingly push you into the truck. Has anyone ever passed the truck and felt like, oh, I got to adjust on the steering wheel here to prevent from being pushed into it? Another example, if you see motorcyclists on the highway, right? Their jackets are always like this. Okay. The reason why is that the air moving past their jackets is moving fast. So faster speed, lower pressure. So it's actually the atmospheric pressure inside their jacket that puffs it out, right? So it pushes from atmospheric pressure inside to lower pressure outside. Okay. There's a million examples of this. Okay. Let's do. Oh, I can show you here. Grab a piece of paper. I can do this with a piece of paper. Just put it on the edge of the table. This is all ratty, but it should still work. Okay, I'm going to blow across the top of it. Faster speed, lower pressure. I don't want to blow into it. Okay, I don't want to be this. Okay, I don't want to blow into it. I want to blow past it. Faster speed, lower pressure. So it lifts up, right? So then the atmospheric pressure underneath lifts it up. It's the same principle with an airplane wing. Obviously, an airplane wing, the air doesn't just move across one side, right? It doesn't just move across the top. But with the shape of the wing, what you do is you manipulate how fast the fluid travels underneath versus how fast it travels over. And if you can get a difference in the speeds, you'll get a difference in the pressures. And obviously, you want to design it so that it lifts the plane. Or you can flip it upside down so it exerts a downward force. That's not useful for planes, but they put these on the back of race cars to make sure that they get driven down into the ground. So you get more normal force, more friction. You can corner and race and stuff better. Okay. What are these called? Spoilers or something? I'm not a car guy. There's a name for these things. Upside down wings. Spoilers. Okay. For any sports fans, a curveball or really any baseball pitch, or most baseball pitches work like this. So let's say looking at a top view of a baseball, VCOM. Well, unless you want it to have a really predictable projectile motion, you've got to do something with it. So what you do is you give it a lot of spin. So along with VCOM, we'll get some omega. I guess I should draw the airflow past it. Like so. And again, I'm going to kind of cheat a little bit and allow a little bit of frictional interaction between the baseball and the air. Because it's not strictly Bernoulli's principle, sometimes this gets called the Magnus effect, if you've ever heard that. This is like if you're really into baseball, you might have heard this. Okay. So I'm going to have the stitching there. That's what creates the interaction between the ball and the airflow. This edge of the baseball is knocking against the airflow, so it reduces the speed of the air and it increases the pressure. So they vary inversely. Whereas over here, this edge of the baseball actually goes with the airflow and gives those air molecules a little extra boost. And if you go to a higher speed, you go to a lower pressure. So the stitching is really important. It's obviously not the original purpose of the stitching. You think in this day and age you can make a ball without having to have stitches on the outside, but if you actually made the balls too smooth, they wouldn't interact with the air as much and you couldn't get as profound of an effect. Okay? Which way is this baseball going to curve? This way, right? Higher pressure on one side versus the other. So this is going to curve, right? We created a lateral pressure differential across the two sides of the baseball as it moves through the air, and that's what gives it its curved path. There are a bunch of baseball pitches. I'm not a baseball guy either, but sinker, slider, curveball, all these things are just how you specifically initiate this curve. The one exception is the knuckleball, which is thrown with no spin whatsoever, and the thing that makes it hard to predict is that it has a kind of an erratic flow through the air. I'm not going to throw a baseball in here, but I'm going to try to throw a beach ball and try to throw a curveball. So if from the top view it's spinning like this, okay, so it's like this, it should curve to the left. Let's try it. Did it curve? Okay. Oh, that was what kind of pitch is that when it lifts like that? Is that a name for that? There's a sinker which curves down, right? So this doesn't curve that well because it's actually a little too smooth. It has these little seams in it, and that's about it. One of my crowning moments as an instructor, I was throwing this in a much larger lecture hall, so I could really kind of give it some serious arm and have it not hit anything, but there was a kid sleeping in the very back row, and I swear I wasn't aiming for him, but it just kind of woke him right up. That's a little bit on the conceptual side. Obviously, examples abound for where this occurs. You're looking at an exchange in pressure and speed. It's counterintuitive because we've been conditioned to think that high pressure somehow implies high speed, but it's not simultaneous, right? High pressure can trade to high speed, okay? So finally, let's just show how we might execute on a calculation. It's actually pretty straightforward because this is ultimately born from the energy method, which we're well familiar with by now. So let's go ahead and just sketch one of those out. So here's a numerical example. You will have several of these on your homework 11 as well. Either they'll be liquids where you can be sure the density is about constant, or they'll be with air, but we're going to have to assume that the air doesn't change density for the purposes of simplicity. Here's my example. I'm going to have a big tank of water. It's going to be 5 meters deep, and there's going to be a hole at the very bottom. And I'm going to put this water tank here on stilts, and that places the bottom of the tank 4 meters above the ground. It's going to be a large tank with a small hole. That's important to establish, and I'll tell you why in just a second. And out of this hole, water is going to flow out like so, And my question is simply going to be, how fast is it going when it impacts the ground? So, just like with energy method, what we would do is we just pick 2 points which are reasonably convenient, and we set the Bernoulli's quantity equal at both of them. This point, obviously, I guess I'll call this point 2. That's going to be one of them, because I want to know the speed there. And then the other one, which I'll, for starters, do is this one, and I'll tell you the significance of that one in just a moment. And let's go ahead and just write out the bookkeeping for Bernoulli's. Okay. So the final point, which I'm calling point 2 here, is pretty straightforward. What's the pressure at point 2? Atmospheric. I'm just out in the air here. Of course, the speed here is what I want to know. And what might I put for the height? 0. It's the lowest height of interest in the problem. So following along with how we normally manage MGH, we kind of bookkeep rho GH the same way. So we'll go ahead and set that to be 0. Okay, so point 1. What is the significance of point 1? Well, this is where the large tank, small hole comes in. Because if I have a gigantic tank with a very small hole, you can pretty much assume that the water is at rest in the vast majority of the tank and only starts to move right next to the hole. So the purpose of picking point 1 was to pick a point where it's far enough back from the hole that I can assume that my acceleration from rest has really not started yet. So I'm going to assume that I don't have any kinetic energy in the fluid at this moment. So Bernoulli's term is not in the kinetic energy term, it's in the other 2. For my height, what should I put in for my height? 4. I'm 4 meters above the ground level at that point. And while I would normally try to solve symbolically, I'm going to put it in as a 4, just so that you can make sure you know what number should be going in there. And then the pressure, is that atmospheric pressure? No, I'm at the bottom of this tank of water, so I luckily have a formula which will tell me how much that is. The pressure at the bottom will be atmospheric pressure plus some more, your gauge pressure. In this case, gauge pressure is rho GD, and what's my D value? 5. I'm 5 meters below the surface when I'm at the bottom of this tank. So that, again, just so you don't mix up H with D, I'll put in one of those is 4 meters and one of them is 5 meters. So let's copy down, of course, substituted a bunch of things. So it's nice to do a line of cleanup every once in a while. PATM plus rho G times 5 plus rho G times 4. I know that looks odd, but let's leave the numbers where they are. Over here, PATM plus 1/2 rho V2 squared. And at this stage, let's start just combining and simplifying. Let me combine these 2 first because they have common terms. So 5 plus 4 is 9 rho G. So I'll have that look like this. I know it looks odd with the number on the end, but hopefully you agree that it's valid. One of the other things you might notice is that atmospheric pressure is on both sides, so we can subtract that off both sides. That's often the case because atmospheric pressure is kind of the baseline that you really are operating off of. You're either at atmospheric pressure or atmospheric pressure plus some more. So The plus some more is the only thing that really ends up creating the pressure differential between one place and another. I can also divide now both sides by the density. Density cancels, and so finally we can solve for V2 is square root of 18g, which I believe is 13.3 or so. That is the speed of the fluid just before impact. So you can see that the structure of it is very similar to an energy conservation problem. And similarly to an energy conservation problem, that is by no means the only option. For instance, let me give you an alternative option. Let me pick that my point 1 was up here instead. So let's find out what that would have looked like. What's the pressure there?
Atmospheric.
Atmospheric. And how much kinetic energy does the water have there? 0, right? Large tank, small hole. So obviously the water level has to be dropping a little bit if the water's coming out over here, but it's approximately 0, right? So we don't have any kinetic energy, and we're at our baseline pressure. Where is all what term is all the stuff in? It's in the potential energy term, right? Because what's the height above the ground level?
9.
It's 9. Well, I'm not going to continue any further because I can already show you that this is exactly the same as this. So it would have worked out exactly the same. In fact, just to give away one of the secrets of Bernoulli's, if I'd taken this water molecule at the top of the tank and I dropped it in free fall, guess how fast it'd be going by the time it hit the ground? 13.3 meters per second. There, of course, it would have done the classic converting from potential energy to kinetic, and it doesn't have a pressure option because it's just falling through the atmosphere. The only thing that Bernoulli's allows us to figure out is that if instead of just a water molecule dropping like a projectile, we can look from here to here. Of course, it's not that it goes faster, it's the pressure that increases, right? So if out in the air here, it's V increasing, but the pressure is constant. Inside the tank, V is constant, but the pressure is increasing. So by the time we get to the bottom of the tank, we have an extra term to slosh into. It's not just kinetic and potential energy. We have pressure to trade with as well. So if we have that at the top, it's mostly in potential energy. At the bottom of the tank, it's mostly in pressure. Obviously, a little bit still in potential energy. And by the time we get out of the hole, we've exchanged what used to be in pressure into kinetic energy. So P trades into KE. Obviously, the height hasn't changed from here to here. And then finally, going from here, just outside the hole, all the way to the ground, we'll exchange the rest of our potential energy into kinetic. So it's, the only difference with this one in free fall is, of course, that it goes straight from potential energy into kinetic energy. It doesn't spend any time being kind of rerouted into pressure instead. OK, so that'll do it for Bernoulli's. That'll do it for moving fluids. That will do it for fluids. That will do it for homework 11. Let me get your exams back.
So this one was 51%, and the last one was 52%. Is that right? What's exam?
This is Physics 111, Exam 2, Fall 15. The mean score was 59 out of 115. That is 51%. Not the best. Like last time, I'll set that to a B plus B-ish. Standard D was quite large, indicating a wide level of different point totals. That is a letter grade. The range of scores was a low of 11 to to a high of 110. And as usual, there's much more on the web. This is just to get you some idea as you walk out the door. Okay, Amy Zhao, Colin Buckley, Gwen Cook.